So I'd like to thank the organizer for the invitation to speak here and the organization. It's been wonderful so far to be here. It's my first time at IMPA. So this is joint work with Mario, who spoke yesterday and tomorrow, but on a different topic, and Oscar Garcia Prada, both from ICMAT Madrid, Vamsi Pingali from Bangalore, and Cheng Zhao from Shanghai Tech. Okay, I want to apply some, I guess, algebra and geometry, no? If that links to the title of the workshop. So I want to apply something. I will spend, since there are so many different backgrounds, some time on the general picture of where my problem is. So I want to apply something I don't know, but I think it makes sense to call this the Kempf-Ness principle. Is it too small or is it okay? Okay? Mm-hmm. Or maybe Attila bot, but Attila and bot have too many things to say. I mean, this is based on a theorem by Kempf-Ness, and Attila and bot may be the ones who observed. It can be applied in different situations. So it's more or less, I mean, I will be very, roughly speaking, say what this is. If you have some PDEs, okay, usually nonlinear PDEs with a some geometry, that can be written as the vanishing condition for a moment map. I guess many people know this, but I don't think everyone do. So a moment map for some action of, and in this case, infinite dimensional group on, I mean, everything is formal here. Formal Kähler, again, infinite dimensional Kähler. And that's the difference with the case Mario was explaining yesterday, manifold. Perhaps you can solve it. Okay? You can solve it's applying geometric invariant theory. What I mean is you can find a condition such that some point in the orbit of X may solve the equation. So perhaps I can say when this is non-vanishing, non-empty, sorry. And the condition is polystability. So I want to apply this in a particular problem. But I think I can try to review some of these concepts and give the main examples and then go to my problem. Okay. Okay, so this is the plan to talk. I will explain this in the first part, then explain where the equations come from, and I will state the problem, find how my problem fits here, and solve it using symplectic reduction by stages. Then I will state the results. So, yeah, this is kind of the framework that I will use. So as I said, GAT can help to solve some very special kinds of PDEs. So I did maybe I'm too ambitious. I want to give a short slide on what GAT is for people who may not come from somewhere around that field. So if you have a complex reductive affine algebraic group acting on a complex projective variety, I mean, there are more general situations in this applies. But let's say we are in this case, and there is a lift to an equivariant, I mean, to an ample line bundle of this action. Okay, we have this situation. Then you say that the point is semi-stable in the sense of GAT if there exists some positive number, some non-vanishing section of this power and the nth power, which is G invariant and doesn't vanish on that point. Okay? So I can cover an open subset of the manifold of the variety with these patches where there are sections like this sigma, and since L is ample, they are affine subschemes. Okay. And then I can glue spec of the G invariance. There is a way Mumford does to do it. Okay? So gluing these affine schemes given by the G invariance, you get a new scheme, which is the GAT quotient. And its points are the orbit. Well, they are not actually the orbits of the semi-stable points. They parameterize the orbits of polystable points, which are the closed orbits inside here. And then there is also a definition of stability, which is imposing a bit more. Now, the orbits have maximal dimension. Okay. And well, this also has. I mean, this is a categorical quotient, if you like. It has some universal property for morphisms, G-invariant morphisms to schemes Y. I mean, they factor. I mean, this quotient factor underline means a factor of points. This is the quotient of one factor of points by the group. Factor action. It factors through some G, no? Okay, for a morphism of schemes. So this is what people call categorical quotient. Okay, so this is what is going to give us the solution to our problem, this theory of Mumford. Okay. Now, I mentioned Kempsness that relates this to symplectic geometry. So in this case, you have more data. You have a maximal compact subgroup, K, and you know, assume X is inside some Pn, okay, CPn, and it's G invariant. Okay, so the line bundle in the last slide is the pullback of O1, if you like, to have something very ample. And assume that you have a representation that gives you the G action, okay, and it restricts the unitary representation of the compact Lie subgroup K. Okay, so in this case, there is an explicit formula for a moment map. Okay, and this is everything finite dimensional. That's the main difference with this principle. Okay, but in this case, Kempsness observed. I mean, it's very nice. They found I mean, they proved more things, so maybe it's a different language, but now this is like two of the things they say you can prove in this framework. So you can answer this question in the finite dimensional case. Okay. So your point has to be polystable to have a solution. And of course, if x is a 0 of the moment map, then you see by this first equivalence that you have this inclusion, and it induces actually a homeomorphism. Okay? So I'll write here. And you have this. You don't even need things to be smooth for this homeomorphism. And the proof they give is based on some functional that, I mean, there is a variational approach to the proof using this functional that in the infinite dimensional case is usually interpreted as some energy. Okay? So now I want to explain what I think are the main examples where this applies. It's very well explained in many papers by Donaldson, I think, and he has applied it many times in the very non-trivial cases. The first one is the Hermitian-Young-Mills equation, and this comes from an observation of Atiyah and Bob. It was very nice. That's why I say it could be Atiyah-Bob principle, because they are the ones that bring the Kempner theorem to solve PDEs. So you start with a Hermitian vector bundle on a Kähler manifold, compact Kähler manifold. And then Atiyah and Bott observed first for surfaces, but it was later applied by Donaldson in higher dimensions. Actually, he proved a theorem in Narcima and Seshadri with in n equals 1. That's his first paper. So, following, yeah. So in this case, you have this the x here is actually this A, the unitary connections. Okay? And there is an action of the gauge group. As there. And there is this formula for the symplectic form. This is one of the terms in the module IM Mario wrote yesterday. Okay. And we are only interested in the zeros, so I won't write explicitly the formula for the moment map. But the equation is this. Okay, where I have to define a few things, I guess. So F is the curvature. So that's a two form with values in few Hermitian endomorphisms of E. And lambda G is the metric. I don't know whether he wrote it, but it is. Actually, it only depends on the symplectic structure, but let's do it. This is the contraction, or if you like, the trace. Okay. So now, if you impose the condition that the connection determines a holomorphic structure on the vector bundle over your complex manifold, then this equation, which is in this case called the Hermitian-Gemills equation or Hermitian-Einstein equation, is satisfied if and only if some condition coming from the other side, from GAT, is satisfied. No? It's called Mumford-Takemoto polystability. So in case n equals 1 was Mumford's stability. Now, so this is the first example, Hermitian-Gemills. And the second main example that is relevant for this talk is a theory started with Yau, who conjectured some kind of stability condition for Kähler metrics that satisfies some canonical, some equation. It's Kähler-Einstein. So in this case, you fix a symplectic, a compact symplectic manifold. And Fujiki first, and Donaldson in some greater generality, observed that the manifold, everything is quite formal, so I will think of this space of complex structures compatible with omega as, defining the Kähler structure as a manifold, even if it's infinite dimensional, has, of course, a canonical action of the group of Hamiltonian symplectomorphisms. There is this formula for a symplectic form, and they observe this is similar to this, to the equation of the Hermitian-Gemills equation, to the Hermitian-Gemills equation. In this case, we had this. Okay, that's the vanishing of the moment map in the previous slide. So in this one, the moment map is the scalar curvature. Okay. And it has been very non-trivial, has taken decades to prove these results of Chen, Donaldson, and Sun, coming from conjecture first by Yau and a lot of contribution by Tian. For instance, the definition of polystability was first Tian's, then it was improved by Donaldson. And it is, again has a GAT interpretation. I wouldn't say, it takes too long even to say that, but let's see. A Fano manifold admits a Kähler-Einstein metric if in the class, in the cohomology class of the tangent, if and only if this polarity is polystable. And actually, in this special case, this condition is Kähler-Einstein is just the vanishing of the moment map. Okay. There is a more general conjecture that hasn't been proved, which corresponds to a possibly non-Fanon. When you don't, when you take any polarization, okay. So I won't. That's a difficult problem, but anyway, this fits here. Okay. Mm-hmm. Okay, so these are the two main examples. And I want to apply or combine them to study another equation, which in a sense is easier. Well, actually, it's much easier than the last one, but still it took us a lot of work. But it's the Einstein-Bogomolny equations. So they come from physics. And they couple on a surface, on a compact surface, they couple, from a physical point of view, a couple gravity, which is a metric, and a binary gauge field, and a Higgs scalar. Okay? And it's supposed to model something called cosmic strings, some kind of cosmic strings produced in the early universe that haven't ever been found. But physicists believe they exist, cosmologists. Okay, so you start with the four manifolds. Space-time with the pseudo-Riemannian metric, unitary connection on a line bundle, Hermitian line bundle, and a smooth section of that line bundle. Then you write the usual Lagrangian, which depends on two parameters, lambda and tau, that they make these hats. And then this is the action, the usual action you write that has symmetry breaking, given by this. Then we are interested in the special case. This is, I mean, solving this is too difficult, I guess. So we assume now that our space-time is some, I don't know, some surface times r in some vertical direction and in time. Don't know. Okay. So I'm interested in the geometry on the surface. That's why I want the metric and the everything, the metric, the connection, and the Higgs field to depend only on the coordinates on the surface. Okay. So if I do that and write the other, I also need to assume lambda is 1, which is like the critical phase of all superconductors between two phases. Otherwise, this is not true. But in this special case, Yi-Sung Yang proved that the early Lagrange equations are equivalent to these three equations. Okay. On the surface. And yeah, as before, f is the curvature, Sg is the scalar curvature, and now we have a new parameter that we are very lucky. Well, we will see later. It is just the gravitational constant up to some factor, the universal gravitational constant. We'll see. To play a role. I don't write the other one, but it just means phi is holomorphic with respect to the holomorphic structure determined by the connection on the line bundle. Okay, so these are the Einstein-Bogomolny equations. That's the name they've given physics. And we will see in a minute that they impose the condition that the genus is 0. So I want to do more other cases, so I will modify a little bit these equations. That's giving us the problem I really want to study. It's slightly more, the equations are a bit different. I mean, the only difference is I will put here any constant. Okay? But I will change a bit the language to more complex geometry. So we start with a compact Riemann surface, but the equations are equivalent, okay? A holomorphic line bundle and a holomorphic section. That's why I dropped the second equation. Okay. Then the equations we started to study like 8 years ago are these. okay, the gravitating vortex equations, are the Einstein-Bogop-Only equations, but they now make sense on any compact Riemann surface. Because, as I said, if C is 0, then genus is 0. Okay, and C is actually determined, and in many other problems of this kind, by the topology and the parameters. It's not free. If you integrate the first equation and multiply by alpha and subtract, then you get this value. Okay. And here, alpha and tau and n are positive. N is the degree of the line bundle. And chi is the Euler characteristic. Okay, so that means that if C is 0, then chi, the Euler characteristic, must be positive, because all of these are positive. So X is CP1. That's why I didn't want to restrict to that case, even though this is the most interesting case. Okay, and there is a lot, because of the physical motivation, there is a lot of work in the mathematical physics and PDE literature until the last few years. Okay, and we want to apply this method to it. Okay, the first thing to do is to observe that the first equation is easier to solve if you fix the scalar metric. If you fix the scalar metric, then the only unknown in the first equation is the gauge field, and the only restriction is this bound. If tau satisfies this condition, then you know there are solutions that they are unique. And there are, by now, a number of proofs of this result. We even have another one in our paper. Okay, so the problem is really in the second one, but actually they are coupled, so that's why we have to do symplectic interaction by stages. Okay. Anyway, in the case in which C is 0, actually, I wanted to say something. There is one part of this equivalence which is easy. You can just integrate. And you see that the first term gives you the degree n of the line bundle. The second is just the L square norm. We are always assuming phi is not 0. It can vanish some points, but it's not 0. So this is positive, and this is the volume. So this obviously implies this inequality. So the difficult part is the converse. Now, the second equation, as I said, is more difficult. But Yisong Yang, the same I said earlier, proved, he studied it with PDE methods he had used with Caffarelli earlier to prove that, you can think of the homomorphic line bundle and homomorphic section as an effective divisor. Okay, this one, G. Okay. And assume that C is 0. That's a topological, we know it implies we're on the true sphere. And assume either of these two conditions, okay? All multiplicities of the points in the divisor are smaller than half of the degree, or there are exactly 2 points with the same multiplicity. Then there are solutions. So, So, Yang said that this is a technical restriction and it wasn't clear whether it was just because the techniques he was using, or whether there was something more fundamental. But I told you about GAT. The point is, they have its meaning in GAT. Okay, so the first means, I mean, the space of effective divisors is this, symmetric power, P1. And this precisely means, if you go to Mumford's book on GAT, that the divisor is stable. Whereas this other condition, the second one, means that it is strictly polystable. That means polystable but not stable. Polystable but not stable, okay? So there must be a reason, and that's what motivated us to study this carefully. So we asked ourselves why. And because of the background we have in this, from previous work, we knew we should try with these methods. Okay? So we apply, this is a T-both observation that we can think of an infinite dimensional version of Kempfness, and maybe you can see that these conditions are precisely, this. So this is the work we did, okay? So to do that, of course, you have to find some infinite dimensional formally Kähler manifold with an infinite dimensional Lie group action, and which is Hamiltonian, find the moment map and prove that the zeros are what we are interested in. So that's what we first or next. I will explain now. So, I mean, this is a summary because of this section. Maybe I can say it. Come from previous works. So these are the gravitating vortex equations we have. And we consider this space of triples. Okay. So T consists of triples given by a complex structure J, a connection, a unitary connection A, and a section of the line bundle. Okay? This is a space that is going to be the Kähler manifold space. Okay, so it's inside space of complex structures compatible with something, I would say, times connections times sections of the line bundle. And we impose conditions like phi has to be holomorphic. Yeah. Mm-hmm. Okay. So I will now explain that there is a group acting on this T with a moment map such that the zeros are the triples that satisfy the equations. So at least formally, we can apply methods of symplectic geometry to construct the moduli space as a symplectic reduction, actually Kähler in this case. Okay, then we can look at the geometry of this and try to prove this to understand the hypothesis of Young's theorem. Okay. So yeah, maybe I can say, I mean, it's too much. Maybe the previous slide is enough. Maybe, I mean, we start with as in the second example, or Yao-Tian-Donaldson theory, we start with a symplectic form, in this case on the surface, compact surface, and the Hermitian line bundle, as in the Hermitian-Gemills equation, but it's rank 1, okay, in this case. There are higher rank cases, but we haven't even tried yet. No? Well, a little bit, but have no results. Well, I think VAMSI does. Okay, some results. Okay. Then, as I said, we can define 3 spaces. The first one, it was already explained. It corresponds to this, the space of complex structures. Second one is the space of connections. And the third one is global sections of the line bundle. And they have these symplectic structures. Okay. Some formulas. And in the Hermitian-Gemills problem, the gauge group was given by automorphisms of the Hermitian line bundle that covered the identity. In the Yao-Tian-Donaldson problem, it was the group of Hamiltonian simplex homomorphisms that acts on the space of complex structures by conjugation. And in this case, we want to merge them, so we need something that's actually a group consisting of automorphisms of the Hermitian line bundle, but covering elements of H. Okay? Now, this is actually a group extension of the other 2 groups. Because, of course, any element of the gauge group is in the extended gauge group, just of the identity. And to any element of G tilde, G, you can attach a G check, which is a Hamiltonian triplet homomorphism. And it's not hard to prove this is surjective. This is a short exact sequence. Okay? The point is that H is inside the identity component of the diffeomorphism group of the surface. Okay? Now, maybe I can skip this slide, but okay. I mean, G tilde acts on J because how does the Hamiltonian simplex homomorphism H? And maybe it's more involved the way there are different ways of thinking about how the extended gauge group acts on connections, but this is one. No? Some conjugation. You look at connections and splitting, but there are other ways. And of course, it acts on sections, on S. Okay? And as I said, well, you impose this condition. And just the 3 symplectic structures with some weights. These are the ones we need. Alpha. And restrict to T, to the space of triples. And then this is, with more details, what I said at the beginning of this section. Okay? So the moduli space of gravitating vortices is this scalar reduction. And there are, I mean, the moment map is very explicit. It's kind of long, but you can write it. But I prefer not to explain everything here. Now, we tried very hard to solve that equation and different strategies, and finally, we realized that since we have this Schrödinger sequence, then maybe the right thing to do is to first, I mean, do symplectic reduction by stages. Okay. First, do the reduction by the normal subgroup, G, and then by the residual action of the quotient H. that's a new, maybe the first new thing we do. Then it becomes very technical. The idea seems simple, but it's quite hard to work with it because, well, let's see. We first perform symplectic reduction by the normal group G. Then we get, I don't know, some M hat. Okay. This group doesn't act on the complex structures, so it's actually infinite dimensional, but the fibers are just the moduli spaces of vortices for a fixed complex structure J. Okay? And that, for each A, is very well understood. Okay? It's a symmetric power of the Riemann surface. Okay. This comes from the theorem I said earlier about the first equation. This one. Okay? The uniqueness part and the existence of the uniqueness part tell you how to solve this. Okay, and then you get this xj is the Riemann surface corresponding to the complex structure J. Okay. Let's see. Now, it was clear. The difficult part comes now. We want to construct. So this is just this. Now, the moduli we want is this. And as I said, we can do it by stages. This is what I said is M hat. Okay. And okay, when you do symplectic reduction by stages, there is a residual action of the quotient group and the moment map. The moment map is this, okay? I mean, it's just very many part of the moment map we started with. But when you study zeros, okay, it's going to be quite difficult, for us at least. I mean, we focus now on that. Then, I mean, the analog in this problem of the orbit space, the orbit of X, is this R. This is observed also by Donaldson in other problems. This is, how to say it, Kähler forms. Omega of some fixed volume that solves this first equation. Some fixed volume. So this is, for some reasons, this is the analog of the orbit in the Kempfner's principle. Okay. Now, the question is whether, given this space, you can find a solution to the remaining equation, the vanishing of the induced moment map, which is, it is this equation. So it is, sorry, no, it is this equation, sorry. Yeah, so it is the scalar curvature of the Kähler metric. If there were nothing else, if alpha was 0, this would be a very classical problem. This is the uniformization theory for Riemann surfaces. But we have this coupling, and we have to plug here the solution H omega to this other equation. Okay, that depends on omega itself. So it's non-local. So okay, symplectic reduction by stages helps us to, in the first step, but now we have a really difficult equation to solve. But okay, we have co-authors that know how to solve them. And that's very good. So here is the strategy. The first part is standard in this principle. So we want to solve this equation. Then, using the moment map, there is a standard method to define a one form on R. Okay, here. I think I call it sigma. Yeah. This is infinite dimensional, but it doesn't matter. Such that it vanishes precisely on the points of R. There are solutions to the equation, to the moment map equation. Okay. And you can prove by this is standard again that this is closed. Where is it? And so it is exact because this R is contractible. So you can write a formula for an integral that we called alpha k energy, or reduced alpha k energy, that corresponds to the energy appearing in Kemp's nest. So that we apply now, I mean, there are several proofs of, especially, I mean, the most difficult part is now, our guide is this other theory, Donaldson, Tian, Yao. And there are many proofs now of this result. And the one we use is a variational approach. It's not the original one of Chen, Donaldson, and Sun. But there is it's highly technical now. There is a way to extend this energy functional to some metric completion, okay, R bar. And there are results by Darvash and Rubinstein, very abstract, that have been applied in the Chen-Donaldson Sun theorem, or in that theory, but you can bring them. Okay. So in particular, we can prove this is when this is proper, and extend a lot of work. Okay. I mean, this slide is really the technical part of the paper. It's what takes longer. So it's, yeah, very brief. But applying these methods, we can now answer our questions. So the main results. First, the technical conditions or the technical restrictions are actually necessary. Okay? This is what we expected, but it was really hard to prove. So if there are solutions to the gravitating vortex equations, then the divisor, the effective divisor corresponding to the line bundle and the Higgs field must be polystable as a point in the symmetric power of CP1 in the usual GAT sense. Okay, and I mean, we started this paper partially because, because we claimed this result in a previous paper, and it was the proof we realized later was wrong. Okay, and it was a shame, and okay, we tried hard to fix it, and it was not possible with the methods of that paper. We had to start again, and that's the beginning of this paper. Okay, so now we hope this is now correct. But since we have now a new method, we can go beyond and prove also some uniqueness and existence result. Yeah, so this is completely new in this theory of Einstein-Bogomolny equations. So in the case of genus greater than or equal to 1, we can prove existence under some assumptions. I mean, this bound is not exactly this one. And in the theorem, we prove something weaker than that, but it's more difficult to, or it's longer, but it's a bit, this is more restrictive. We expect we can prove more, but so far we can't. Okay, but at least we have a uniqueness results for effective bounds. And we also have uniqueness results, and all these theorems are based on techniques used for the Kane-Einstein problem, okay? Adapted with this new non-local term. And again, if the genus is greater than or equal to 1, or the genus 0, and vanishes, the phi vanishes at least 3 points, so this is a kind of rigid, then solutions are unique. Okay, so these are the main results of the paper. Now, using, I guess, the existence result of Yang, Yisong-Yang, the abstraction in genus 0, and the uniqueness, we can find this bijection. And we expect, but I think it's not difficult, but we are really exhausted. This is actually homeomorphism, as in the second part of the Chemnitz theory I told you. Okay? Okay. Now, we can think a bit about this GAT quotient. You know, this parameterizes binary forms. They used to be called binary quantics. They are, the nth symmetric power of P1 is Pn, no? Where Pn is parameterizing this kind of polynomials. Okay, and this is a very classical problem from the 19th century. Okay, and there has been a lot of, work in that century by Sylvester and other people. So we kind of link our problem to this. We were very happy. Finally, the moduli space is the moduli of binary quintics. So we have algebra and geometry, and that's what I wanted in this. So thank you.